Thank you. And Steve, you are up.
Thank you, Howard. So again, my name is Steve Moore. I'm a senior engineer for Atlantic Testing Laboratories. I've been with ATL for about 16 years. Before that, I spent about 10 years in the oil and gas industry doing oil and gas exploration. So Howard went over a couple of housekeeping rules, ground rules already, but a couple more I want to mention. Questions, as Howard said, please use the chat feature, and we will address those at the end of the presentation, and we'll get to as many as we can based on time. 100% participation is required to receive PDH credit. There will be some questions throughout. Submit your answers when prompted, and there is a time limit to submit your answer. It's probably about 30 seconds or so, so you should have plenty of time. And you must be registered to receive credit. So you had to have clicked on the register button as an individual to receive credit. So if there's multiple people sitting together with just one individual registered, those other individuals should register to receive the credit. So topics, we'll have a brief introduction on concrete. I didn't coin the phrase the bread of the construction industry, but I like it. We'll talk about the 5 essentials of quality concrete, or what I feel are the 5 essentials of quality concrete. Then we'll get into the cold weather concreting, which is kind of the meat and potatoes of the presentation. And it's really based on 2 ACI documents. One of them is 306, 306R, and the other is 306.1. 306R is it's kind of a guideline to cold weather concreting. 306.1 are ACI specifications, so you can actually take those specifications of that document 306.1 and include it in a project specification. The 306 document was renewed in 2016. Some of the tables that I'm going to show, the table numbers may have changed a little bit, but the information in the tables, the data in the tables hasn't changed. That's why I've got the 306.10 reference there. And then 306.1 was reapproved in 2002. I think that's the latest reapproval of 306.1. And then at the end, we'll talk about concrete maturity or the maturity method, which is ASTM C1074. That's the procedure for estimating concrete strength using the maturity method. So the bread of the construction industry. Again, I kind of like this phrase. I don't know who coined it, but I like it. You know, we think of bread as kind of a staple, you know, a dietary staple, and concrete is really kind of a construction staple. Just about every construction project uses concrete, either new concrete, maybe existing concrete. So it's definitely a staple in the construction industry, and the most widely used or second most widely used substance in the world probably by both mass and volume. And here volumetrically we see kind of general breakdown of concrete, about 6% air. Obviously, if it's air entrained, concrete always has air in it, even if it's not air entrained. Probably has you know, maybe 2 or 3% air. 11% Portland cement, or you know, maybe a portion of that might be fly ash or slag or something like that. 41% gravel or crushed stone, that's a coarse aggregate. 26% sand or fine aggregate, and about 16% water. Again, that's, you know, that's going to change based on the mix. These are just general proportions, but those are pretty good numbers. So 5 essentials of quality concrete, and these are what I consider to be essential. You got to have suitable materials. And it's important that the materials be compatible. You want to make sure that, you know, there's a lot of chemistry going on in concrete. and you want to make sure that all those materials are compatible. You don't have ASR, alkali silica reactivity going on, with your cement fighting your coarse or fine aggregates. You don't want admixtures fighting each other. Some admixtures are not compatible. So it's kind of like garbage in, garbage out. If you don't have good materials going into your concrete, you're not going to have a good durable product. Proportioning, mixing, transporting. Some people forget about transporting, but that's pretty important. I'm here in the Albany, New York area. We've got some projects sometimes that are up in the Adirondacks, and there's no ready mix suppliers up in the Adirondacks. So sometimes just getting one way to the project is close to 90 minutes. So consider proportioning, mixing, and transporting the concrete as part of an essential, one of the essentials of quality concrete. Placing and consolidation, obviously it's got to be placed properly, got to be consolidated. Finishing and jointing, very important for flat work. You want to finish it properly, put the joints, make sure the joints are spaced properly. This could be construction joints, saw cut joints, tool joints, whatever. But make sure those joints are placed properly. And the last one is curing. Obviously, after we got out the first floor, we don't just pick up and walk away. Depending on the temperature, what time of year it is, there may be some pretty significant changes in how the concrete needs to cure. So getting into cold weather, there's kind of two different definitions. ACI has two different definitions, and they're different in the two documents that I mentioned. 306.1, again, those are the specifications, ACI specifications, and they define cold weather as 3 consecutive days of average temperature below 40 degrees. And that's just the arithmetic average. What's the high, what's the low, add them together, divide it by 2, and then you get your average. So it's not a weighted average. And it's less than 50 degrees for half of any 24-hour period. So both of those conditions need to be met for, again, 306.1 specifications to be considered cold weather. ACI 306, which is more of kind of a guidance document, they define cold weather a little bit differently as when the air temperature has fallen to or is expected to fall below 40 degrees during the protection period. So a little bit different definition there, but we see 40 degrees is kind of common. So, that's kind of the benchmark that most people use for cold weather concrete is right around 40 degrees. But obviously, again, you got to take into consideration overall temperature, going to, less than 50 degrees for half of the 24-hour period, or what your anticipated temperatures are going to be for the next 3 days, 5 days, 7 days, or whatever your protection period is. So why are we talking about cold weather concreting? As I said, I'm in the Albany, New York area, central New York. Construction doesn't stop during the wintertime. We have a lot of construction that continues during the wintertime. And we've got some cold weather. Obviously, it gets below 40 degrees. This project here that you're looking at is a local project to the Albany area. I'm going to be showing a bunch of pictures for this project. I believe it began construction the week after Christmas, so in between Christmas and New Year's. They broke ground and started digging for footings and pushing dirt around and things like that. So, January, February, right when they were in the meat of concrete placements, there was some really, really cold temperatures. And a lot of these pictures that I'm going to be showing, I took, and I was bundled up pretty good. It was cold. I think it was 4 degrees on one of these days. So this is another project right on the shore of Lake Champlain. I wasn't involved with this project, but I'll show a couple of pictures of this project too. So ACI 306 has got a handful of main objectives. I did reference 306.16 They added a few objectives between 2016 and 2010. Certainly a primary objective is to prevent early age damage due to freezing. We want to make sure that we're getting adequate strength gain during and after construction. We want to maintain curing conditions that promote adequate strength development, proper strength development, and that it's within 20 degrees of table 5.1. We'll talk about table 5.1 here in a minute. We want to limit rapid temperature changes, which may cause cracks due to thermal stress. And we want to provide a protection that's consistent with the design and durability of the structure. That last bullet there, that means that we might be protecting a warehouse slab on grade or an exterior sidewalk or something like that a little bit differently than like a bridge pier or a bridge deck or something like that. So we want to take into consideration what the end use of the structure is. So some things for preventing early age damage: protection and planning. I can't stress that enough. Planning probably should have gone first, because you can't really protect the concrete properly without planning to protect it properly. And what the short-term goal is, we want to make sure that the concrete gets to at least 500 psi. That's going to offer us one cycle of freeze-thaw protection. That usually happens about 24 to 48 hours after placement, assuming we're at 55 degrees, and you'll see that 50-55 degree range in a couple of different spots. But if we can get to 500 psi, we're beyond what's called the critical saturation point. Hopefully out of that vulnerable stage when the concrete is critically saturated. If you've got multiple freeze-thaw cycles that you're going to be going through, obviously you need a little bit more strength than that, maybe significantly more strength than that. But initially, short term, 24, 48 hours, we really need to get to that 500 psi. We really need to protect the concrete, because that's when it's most vulnerable. So 306.1, again, these are the specifications. So if your project references these are requirements. And ACI requires that concrete be air entrained if it's exposed to freezing and thawing during construction periods. And obviously that's important to slabs and flat work. Maybe it's an interior slab that's going on the project, but if it's placed in January or February, it's going to experience some freeze-thaw cycles. And if it's not air entrained, it's probably going to get damaged. So air entraining concrete, even though it might not be exposed during the service period, is a requirement by ACI. Additional requirements want to make sure the temperature of massive embedments is above 32 degrees. ACI doesn't define what massive embedments are, so those should probably be defined. Is it a number 8 size bar or a number 11 bar? 3/4 inch Nelson stud, whatever. But those massive embedments should be defined. And then thawed subgrade, frost removal from all reinforcement. ACI does not allow concrete placement on frozen subgrade. So we want to make sure that we're warming up the subgrade, and there's different methods to do that. Here's that project that's on Lake Champlain. I'm going to use my cursor every now and then to point some things out. You can see they got some blankets down here. It's kind of hard to see, but there's some glycol heating lines. So what this contractor did was they heated up the subgrade. They put blankets over it. They kept the glycol heaters on for a couple of days to make sure all the frost was out of the subgrade. Got a little bit of protection here from wind. They've got some additional heaters in here. So there was some planning that went into this, and eventually this was a good sound placement. So here we got table 5.1. This is an ACI 306. So these are kind of guidelines. These aren't requirements, specified requirements, but they're guidelines, recommendations. I believe 5.1 is the same table number in 306.16, but this is from 306 from 2010. So what we've got here is we got a couple of different temperatures during placement and protection that we need to consider. Minimum concrete temperature as placed and maintained. It's going to vary based on the size of or what the minimum dimension of your concrete placement is. Whatever element is being placed. So if we've got, say, we've got an 8-inch, 6-inch, 8-inch slab, or maybe a 10-inch wall or something like that, we need to maintain a minimum concrete temperature. Place it at 55 degrees minimum and maintain it at 55 degrees for the protection period. And we'll talk about that protection period here in a minute. Larger dimensions, 12-inch wall, 20-inch wall, 18-inch wall, something like that. You can go down a little bit in temperature. This is 50 degrees. As your minimum dimension gets bigger, and this is just kind of a truncated table from ACI. This temperature can go down a little bit. If you've got say for mass concrete that's 72 inches or something like that. So these temperatures do change as these dimensions change. So here's your concrete temperature. That's again, these are recommendations, recommended mixed temperatures. If your ambient air temperature is above 30 degrees, again, we're kind of assuming that we're in a cold weather situation. So we're below 40 degrees, so kind of between 30 and 40 degrees. Mixed temperature for less than 12-inch minimum dimension, 60 degrees, 55 degrees for 12 to 36. Again, these numbers go down a little bit as your dimensions go up. As your temperatures go down, your air temperatures go down, your mixed temperature goes up. So here, less than 12-inch section, we've got 65 degrees, 60 degrees if we're below zero, 70 degrees and 65 degrees. So if it's below zero, you're asking yourself, well, how do I get my concrete to 70 degrees? This is a graph, I believe, from the Portland Cement Association that shows us what the temperature rise of concrete is related to material temperature. So you can raise the temperature of your cement, water, or aggregates to increase the temperature, the overall temperature of your concrete. The greater the slope of this line, the more bang you're going to get for your buck. So obviously heating up your aggregates is going to give you, is going to have a higher impact on your overall mixed temperature than the water or the cement. So you kind of use this chart as a guideline. Water is probably the most often of these three. Water is what's most often heated up to increase your mixed temperature. What I find kind of funny about this table is, so we've got Celsius down here at the bottom. This last data point here, and it's probably a theoretical point, but this last data point here is above 100 degrees Celsius. I certainly would not recommend adding boiling water to your concrete. But the biggest takeaway here is heating up the aggregates. That's what's going to give you the biggest bang for your buck when you got to increase your mixed temperature. But again, water is probably the most common thing that's heated up. So here we've got question number 1. Question 1 should be true or false. ACI allows concrete to be placed on frozen subgrade.
Okay, Steve, go ahead.
Thanks, Howard. So again, true or false, ACI allows concrete to be placed on frozen subgrade. That, of course, is false. 306 recommends that it not be placed on frozen subgrade, and 306.1, the ACI specifications, they don't allow it. So here's table 7.1, and this is the protection period that I'd mentioned previously. And this is these are the number of days that the placement needs to be protected at the minimum temperature on line 1 from table 5.1. That's that 55 degrees, depending on your member thickness. You can see here you can gain a little bit of time if you're using accelerated set concrete. Accelerated set concrete can be either using an accelerating admixture or perhaps a type 3 high early cement. So depending on the service condition, it gives us, again, these are recommendations. This is 306, not 306.1. It gives us recommendations for protection, the number of days for protection. This no load, not exposed, by the way, the load that they're referring to here is during the curing period. So this is during the first 28 days. Is this going to see a load? And this exposure is during the service period. So this line 1 here could be maybe it's a footing that's down below the frost level. You know, footing is not going to see, probably not going to see a load, or at least not much of a load during the curing period, and it's not going to be exposed to freeze thaw. You know, assuming it's down below the frost line. So that's the loading and exposure conditions. No load, exposed, we've got a higher protection period. Partial load, exposed, we've got 6 days protection period. And then this full load down here, it directs us to chapter 8, and I will discuss that. In a minute. But again, when you're looking at this table, just remember, and 306 tells you this, but just remember what these loading conditions are. It's during the curing period, and this exposure is during service. So we've got our placement temperatures, we've got our protection period. We're in a cold weather situation. How do we protect it? ACI 306 is a great document. It's got a lot of guidance, and this is a table in 306. This is actually from 306.10. The data is the same in 306.16, but it's presented a little bit differently. But the data is the same. So what this table shows is what our minimum exposure temperatures can be for concrete slabs above ground and walls and surface temperatures maintained at 50 degrees. So all of these numbers that we're seeing here are air temperatures. And this first column has got wall or slab thicknesses. We'll use inches. And then each one of these sections is based on cement content. So if our concrete mix had 300 pounds per cubic yard of cement, we would use this one, you know, this portion of the table right here. What I've got highlighted is concrete mix design with 500 pounds per cubic yard. You know, that's probably a typical 4,000, 4,500 PSI concrete mix. And what I've got highlighted here in this table is we want to place a 12-inch wall. We anticipate that our air temperature, that our minimum air temperature is going to get down to 3 degrees during our protection period. Okay, we know what our protection period is, 2 days, 3 days, 6 days, whatever. So during that protection period, it's going to get down to 3 degrees. Now up here at the top, This tells us the R value that we need to maintain the concrete at 50 degrees, up here at the top, 50 degrees for 3 days. So if we're placing a 12-inch wall with 500 PSI concrete, it's going to get down to 3 degrees within the next 3 days to maintain 50 degrees on the surface of the concrete. We need to provide an R value of 6. That doesn't seem like much. And what we're doing here is we're using the heat of hydration in the cement. So as the cement hydrates, it's an exothermic reaction. It creates heat. We're using that heat to protect the concrete, to keep the concrete at that minimum temperature. By protecting it, covering it with material that has an R value of 6, in theory, we should be able to place our concrete and 3 degree with the air temperature down to 3 degrees. Basically, that project that I showed you earlier, that's what they were doing. They anticipated single-digit, above zero, single-digit temperatures. They were placing 12-inch walls. Their cement content, I think it was 560 pounds per cubic yard or something like that. They were covering everything up with blankets that had an R value of 6. So you think to yourself, all right, what are the different R values? 30610 has got these different R values. This is per 1 inch. So 1 inch of expanded polyurethane has got an R value of 6.25. So in theory, we could just put 1 inch of expanded polyurethane and get our value of 6. Glass fibers 4, mineral fibers 3.46. These are probably the 2 most common ones that we see in most concrete curing blankets, are these mineral fibers. Also, the previous table assumes steel forms. So if you're using 3/4 inch plywood forms, then you're already giving yourself an R value of about 1. So here's a couple of blankets. Sure, everybody's seen these, all different colors, sizes, types, fillers. But what a lot of people don't know is down here in the corner, a lot of these blankets, they give you the R value. So if you need if you need an R value of 6, you can take a look at these tags, and if it's a blanket specifically for concrete curing, and it's not some other type of blanket, it'll typically have an R value here. Just be aware that R value might be it might reference per inch, and the blanket itself might not be 1 inch thick. So you just got to be aware when you're looking at those. But most of these tags do have R values on them. So we're up to question 2. Question 2 should be true or false. ECI 306.1 requires concrete that will be subjected to freezing during the construction period to be air entrained. Again, that's 306.1. Those are the ACI specifications.
Steve, go ahead.
Thanks, Howard. So that is true. Again, just because it's an interior floor slab, or it's going to have interior service. If it's placed during the wintertime and it's going to be subject to freezing weather, it really needs to be air entrained to protect it during that period. So here's that same project outside of Albany. Here we've got a couple of pier footings that are covered up with blankets. We've got a heater providing heat in here. There's no concrete under here. These have not been placed. What they're doing here is they're heating up, thawing out, everything, making sure that there's no frost on the reinforcement, making sure all the frost is out of the ground. It's kind of hard to tell, but here in the foreground, I mean, this looks like concrete right here. This is frozen. This is frozen soil. This is one of those single-digit days. And look around. They were planning for this. They got a whole bunch of blankets over here. They got a whole bunch of blankets over here. This contractor did a really good job. Here we see a column pier that's already been placed. It's covered up with blankets. These blankets have an R value of, I believe it was like 2.6 or 2.8 or something like that. So multiple blankets, to get up to that 6 R value. What you can't see here is we've got some cylinders that are placed up under this, up under here for field cure cylinders. So, so the engineer and everyone can get an idea of how effective this protection was. Over here to the right, it's hard to see because they're under these blankets, but there's actually some glycol heating lines coming under here that are just down, wrapped around the bottom of this placement. But again, look around. We got more blankets over here. That heater over there heating up that that pier footing and this pier footing. Here's a foundation wall, 12-inch foundation wall covered up nice and tight. Pay attention to the corners. Corners are very susceptible to, that thermal stress and thermal cracking. So you want to make sure you got your corners wrapped up really well. This is probably a return line for the glycol heating system that they've got that runs along the line of this wall. Again, a lot of activity going on out here and lots of really good planning. This is the same project. This is the wall in the previous picture. It's not the same day, but this is the same wall. This was taken from a drone, and it really shows the level of planning and the equipment that the contractors got. They've got, a glycol heating unit here, glycol heating unit here, a glycol unit here, blankets all over the place, here. And they've actually got blankets wrapped over these glycol lines here, going to all these different placements. So all of these placements were done on the same day, and all of these heating lines are kind of going to all these placements, and they've got them covered up with blankets. So again, that's the planning portion. This is not something that you just pull together overnight. And this is a Mohawk River over here, and all that is ice. So it's cold. So we know our temperature, the temperatures that we need when mixing, placing, protecting. We know how long we got to protect them. Now we want to avoid rapid temperature changes. Again, this is where that thermal shock comes in. Concrete is, in some ways it's like a ceramic, so it's really, really vulnerable to thermal shock and cracks due to thermal shock. So we want to cool it gradually or warm it gradually. Remove the heat slowly if you've got heat on there. The blankets, take the blankets off slowly. Don't just pull all of them off at the same time, or just leave them in place until the surface temperature stabilizes with the ambient temperature. or just pull them off as you need them. That's what the contractor on this other project did. When they needed blankets, they either took some that were laying on the ground, or they went back to the oldest placement and started taking blankets off of the oldest placement. So here's another kind of a truncated table from both 306.1 and 306R. So this is, there is a specification that allows for a maximum temperature drop in a 24-hour period. And it's based on the section size, a minimum section size. So you can't have, your maximum allowable temperature drop for a section less than 12 inches in minimum dimension. You can have up to a 50 degree temperature drop. As your section gets larger, it's going to be more susceptible to large temperature changes and that thermal shock. So the allowable temperature drop actually decreases as your section size increases. And again, this is both from 306.1, so that's a specification requirement, as well as just a general guideline. And we're up to question 3. Question 3 asks, do we need to control the rate at which we allow the temperature to drop at the end of the protection period?
Steve?
Thanks, Howard. So the answer is yes, we need to control that rate. And again, it changes based on the size of the minimum dimension size. And we're trying to prevent thermal shock. So this is the previous table we were looking at that talked about what our protection period, our recommended protection period is based on our loading and exposure condition. And I mentioned down here about the full load, and it directs us to Chapter 8. Chapter 8 in 306 says that if you're going to be putting a full load on the member, and maybe this is, maybe you're removing forms. It could be any kind of full load, a column load on a pier or whatever. But it directs us to Chapter 8, and Chapter 8 says that we've got to do some additional testing. It can be non-destructive testing or destructive testing. You take a core out of the element, rebound hammer, Windsor probe, something like that. But we got to do a little bit more than we're putting a full load on it. So we want to understand what that strength is. And one of the methods in Chapter 8 mentions the maturity method. And what the maturity method is, it's a way of estimating concrete strength based on the time and temperature, based on the curing conditions of the concrete. The ASTM C1074. And the primary concepts are pretty easy to understand. It says that a given combination of curing time and concrete temperature will result in a specific strength for a given concrete mixture. Concrete strength is a function of time and temperature, and cold concrete develops strength much slower. So all of these, it's basically pointing to concrete strength being a function of time and temperature. And for the most part, I think we all understand that. So there's a couple of different maturity functions that we'll talk about. This is the Nurse-Saul equation. This is probably the most common one. And it's basically a summation of your temperatures over time. So T sub A is the average concrete temperature during the time interval, and T sub 0 is what we call the datum temperature, and that's a temperature at which strength development stops. That's going to be a little bit different for every mixture for different types of cement. Generally, it's taken to be anywhere from 0 to 5 degrees Celsius. The appendix for the maturity method does give some guidance on on what to use for datum temperature. So that last maturity function, the time temperature factor, Saul, that equation was a Nurse-Saul equation. Saul came up with a statement that basically says concrete of the same mix at the same maturity, again, maturity being a product of time and temperature, has approximately the same strength, whatever combination of temperature and time go to make up that maturity. So if we think about the product of two numbers, 5 times 10 is the same as 10 times 5. So if you think about this in maturity function, 5 days at 10 degrees Celsius will theoretically give you the same strength as 10 days at 5 degrees Celsius. The other maturity function is called the equivalent age factor, and this one's a little bit different. It's a number of days or hours at a specified temperature. So here we're keeping the temperature constant. Specified temperature required to produce a maturity equal to the maturity achieved by a curing period at temperatures different from the specified temperature. It's hard to understand that, but the general application is what we're doing is we're comparing concrete cured in the field at different temperatures, fluctuating temperatures, to concrete cured in the laboratory at a specified temperature, or concrete temperature, or constant temperature. This function's a little bit different. It's got this funky nonlinear exponential thing going on here. T sub E is the equivalent age at T sub S hours. So whatever number of hours it is. Q is the activation energy divided by the gas constant. These are in units of Kelvin. The time is in units of hours. Again, the appendix kind of gives a little bit of guidance on values to use for Q. T sub A is the average concrete temperature during the period or over time, and T sub S is a specified temperature. So this would be, say the temperature in the lab. This is based on the Arrhenius equation, and if anybody remembers the Arrhenius equation from chemistry, it predicts the rate of a chemical reaction. And so, it's easy to see how this can be applicable to concrete curing. Obviously it's a chemical reaction, the hydration of the cement. So how do we apply the maturity method? It starts in the lab, and it has to start in the lab. We cast and cure a minimum of 15 cylinders. It has to be the same mix that we're using out in the field. So if this is a mix for a foundation wall, we mix that in the lab. We make some cylinders. We place maturity sensors in at least 2 of the cylinders, and then we test 2 or 3 cylinders at multiple ages, 1, 3, 7, 14, and 28 days. And then we plot the compressive strength and the maturity index. We get that maturity index, those maturity values. We get that from the sensors that we put in the 2 cylinders. And we're not breaking these 2 cylinders. These 2 cylinders, they stay in the same curing conditions as the other cylinders that we're going to break. So when we break the cylinder at 1 day, we download the data logger from the 2 data loggers from the 2 cylinders, and we see what that maturity function is. If you have a high early mix, you might need to test these cylinders more frequently. We've had to do it in 3-hour increments up to 24 hours for some high early mixes. So just be aware that these testing intervals may be different based on the mix that you're placing. So when we break the cylinders, we plot the curve. We get something like this. We've got maturity down here at the bottom again, just a product of time and temperature, and compressive strength here on the y-axis, and you get a curve that looks very similar to this. Now, what we do in the field, again, that maturity index has to be established in the laboratory. That curve on the last slide, that has to happen in the laboratory before you can apply any of this in the field. So you take the same maturity sensors prior to placement, and you put them at different locations, maybe critical locations. You know, again, maybe you're loading up a pier or footing or something like that. You want to make sure that it's not touching any reinforcement, especially any reinforcement that may be exposed. Maybe you've got some embedded bars in the pier footing or in the pier that are exposed to air. You want to make sure that your sensor isn't touching any reinforcement. Then you monitor the maturity index from the probe that's installed in the field, and based on the maturity index, you go back to this curve. So if we've got a maturity of, say, 15,000 Celsius degree hours, in theory, our compressive strength would be, you know, somewhere between 4,000 and 4,500 psi. So we establish this curve, and then the sensors that are in the field, we just figure out what the maturity value is from the sensor in the field, and then we go to this plot again that was established in the laboratory, and we figure out what the estimated compressive strength is. If there is any, maybe there's some critical placement operations. You know, again, these are all theoretical. You know, it's based on pretty sound science. But if you've got a critical operation, maybe you want to consider something other than just a maturity method. You know, something, you know, it could be rebound hammer, it could be Windsor probe, maybe field pure cylinders out in the field, something like that. But or maybe you can take cores out of it. But I don't think anybody likes to core brand new concrete. So we're up to question number 4. Question 4 should read, what are the 2 parameters that we measure for maturity functions?
Hey, Steve, go ahead.
Thanks, Howard. So hopefully everybody got time and temperature. Those are the 2 parameters that we're measuring for the maturity function. Ultimately, we want to know what the compressive strength is, but the parameters we're measuring are time and temperature. So we've got another question, question number 5. This should be a true-false question. The equivalent age maturity function assumes that concrete strength gain is linear based on time and temperature.
Go ahead, Steve.
Thanks, Howard. So that is false. It's not linear. It is based on the Arrhenius equation, and that's the one that's got that exponential function in it. So a couple of final considerations, mainly related to cold weather concrete and placing concrete in cold weather. Planning, preparation, both very critical, and by the way, planning. Again, this is not placing concrete in single-digit temperatures is not something that you can't plan for, and that planning probably should take place weeks ahead. So if you know that you're going to be placing concrete in January, February in central New York, you should be planning for it weeks ahead of time. So that concludes the presentation. Not sure if anybody has submitted any questions through the chat feature. We're doing pretty good on time. So Howard, if you got some questions there, I'd be happy to answer.
I do, Steve. We do have a few. The first one is, does the ACI specify the size of the massive embedments?
It does not. And I will say one thing that I didn't do is look at ACI 306.16. So 306.1 is what talks about massive embedments, and it does not give the size in 306.1. 306.16 may have some more guidance on that, but I think probably not. You really want to make sure that nothing is going to be frozen. So you want to have everything above 32 degrees. That's really the big takeaway.
Okay, next question. Are there different temperature requirements for thick foundations, such as for a wind turbine? There are, but recall those 306 is what has the different temperature recommendations. Wind turbine foundations are going to be considered mass concrete placements, and there's definitely going to be some considerations for controlling temperature. Not only controlling temperature of the heat of hydration, maybe having some fly ash or slag or something that has a lower heat of hydration, but also that after the protection period, allowing the concrete to come up to ambient temperatures, and because it's going to be a massive, probably more than 4, 6, or even 8 feet thick, it's going to be a pretty low temperature differential. Okay, next question. For LEED projects, LEED, what is the most energy efficient or encouraged concrete mixture element to be heated? And then the second part, does LEED count the heating of the poured mixture elements towards its point count?
I don't have any LEED accreditations myself, so I don't know that I can really answer that question. It's going to come down to what's more efficient to either maintain the concrete temperature or to bring the concrete temperature, the concrete mix temperature up to the minimum required temperature. Certainly, the most efficient way to maintain the placement temperature is using blankets, and you can go up in R value, just because it recommends an R value of 6. You can go higher than that, but that's certainly going to be the most efficient, the efficient way to control the temperature. As far as other ways that may be LEED accredited or help for LEED accreditation, I'm not really sure.
Okay. The maturity method implies that you do the lab work first before you pour it in the field, correct?
That is correct. And how long before is going to depend on the mix. If you want to get a maturity, if you want your maturity function to go out to 28 days, obviously you need to have 28 days under your belt before doing any placement in the field. We see the maturity method used most often for early placements. You know, when they want to either remove the protection period or forms or something like that. You know, put something into service early. So a lot of times when we develop that maturity function, we might only go out 7 days. But the answer is yes. It's got to be done in the lab ahead of time. How much ahead of time depends on the project.
Do you have a preference in performance between formed and saw cut control joints?
I don't. It's really based on timing. I prefer tooled, formed joints myself, but your timing's got to be right. If you wait too long, then you're going to be fighting with it. Same thing with saw cut joints. You can't wait too long to saw cut the joint. So timing is critical either way, depending on how you're going to do it.
Can concrete experience one freeze-thaw cycle and not lose much strength?
Yes, provided it has a minimum strength of 500 psi prior to that one freeze-thaw cycle. Additional freeze-thaw cycles, to be durable for additional freeze-thaw cycles, requires additional strength.
Do the glycol heating systems utilize propylene or ethylene glycol?
I don't know. I would guess ethylene glycol, but I don't know. They could probably use both.
And that was the last question, Steve.
Okay.